laptop to actually get this thing to work, apparently involving fixing permissions, which I thought was only a thing that I didn't think that was a thing in Mac. I thought that was like just a Windows thing where I had to like defrag the permission thing or whatever. Anyway, let's talk about graphs. Okay, so 6 Degrees of Kevin Bacon. This is that really fun game / really interesting game where we try to figure out if every actor can be linked to Kevin Bacon in 6 steps or fewer. And so the way this game is played, there's a connection between 2 actors if they were in a film together. And so, for example, if we want to link Kevin Bacon and Carrie Fisher, we could say, well, Kevin Bacon was in Flatliners with Julia Roberts, who was in Pretty Woman with Richard Gere, who was in Arthur with Sean Connery, who was in Indiana Jones and the Last Crusade with Harrison Ford, who was in Star Wars with Carrie Fisher. So we're able to link Kevin Bacon with Carrie Fisher in 5 steps. And so this is a really fun game based on one of the Stanley Milgram, the famous psychologist, based on one of his studies from the 1960s where he sent letters to a bunch of people in, I think it was Nebraska, and they had addresses of people in Boston, and they had to get the letter to the person in Boston. Now, of course, this was in the 60s, so there was like no internet, and it's not that easy to get a hold of like a Boston area phone book. So what you would do is if you didn't know the person in Boston, you would send it to somebody that you thought might know somebody who could get it to that person in Boston. So if you're in Nebraska, you might send it to a friend in, Indiana, who would send it to somebody in Ohio, who would send it to somebody in Rhode Island, and then eventually it would get there. And the number of steps for this to happen was about 6. And in fact, a lot of people sort of guess that everyone in the world is connected by 6 steps or fewer. So somebody who knows somebody who knows somebody, to the 6th power, a person that lives in a yurt in Mongolia or something like that. So this is often known as like the small world theorem. And so it's fun to do this with movies. This game, by the way, was actually created by a couple of students at Albright College in Reading, Pennsylvania, where one of our chemistry faculty, okay, full disclosure, my wife Helen, actually taught for a year. Lovely school, lovely claim to fame. Not nearly as awesome as Knox, though. Let's be serious. So, what's interesting about this ability to connect people in some number of links is we can actually do this differently. We can get Kevin Bacon to Carrie Fisher in only 3 links, because Kevin Bacon was in Apollo 13 with Tom Hanks, who was in Dragnet with Dan Aykroyd, who was in Blues Brothers with Carrie Fisher. So we could sort of do it in 3 links. It might be possible to do in 2. I don't think Kevin Bacon and Carrie Fisher have ever directly been in a movie together, in which case we could get it in sort of 1 link, or I guess technically maybe 0 links. But we can sort of do this differently. And so this actually is a graph, believe it or not. It's a great way to represent sort of linked information or information about relationships between nodes or vertices. So we're going to say that each actor is a node or a vertex. And if 2 actors were in at least 1 movie together, we're going to say there's an edge between those 2 nodes. And so we can sort of build up a big graph of being in movies together, relationships for all of these actors. So this is just a really simplified example, and there's a bunch of links that are missing in here. But, you can sort of see, like, Kevin Bacon was in a movie with Kiefer Sutherland. Of course, I can't remember what movie it was. Obviously was in Flatliners with Julia Roberts, who was in Pretty Woman with Richard Gere, who was in, Arthur with, or maybe, I don't remember what it was called. I think it was called Arthur, with Sean Connery, who's, connected to Harrison Ford. Sean Connery was in, I think, The Rock, maybe, with Wesley Snipes. Wesley Snipes was in something with somebody named Charlie. Now this is beyond my ability to... I did this chart a few years ago. But anyway, there's a bunch of links in here missing, but there's a bunch of links that are in here, and you can kind of see this graph idea. These are nodes. These are edges. Kiefer Sutherland was in Lost Boys with Corey Feldman and Corey Haim. Fantastic movie. Good time of year here in October to go ahead and watch it. So this is a visual representation of this sort of connectedness. Graphs can be weighted or unweighted. If you have unlabeled edges, we're going to call this an unweighted graph. So implicitly, everything has a cost of 1 or some uniform cost. For this graph example, we could say I don't care how many movies you were in. We're just going to make it an unweighted graph. You're in at least one movie together. We also could weight the edges with the number of films two actors have appeared in together. So, for example, Tom Hanks and Meg Ryan would have a weight of at least 2. Their edge would be weighted at 2 because they were in Sleepless in Seattle and You've Got Mail together and possibly other movies I can't remember. There would be at least 3 for the weighting of the link between Alec Guinness and Carrie Fisher to represent all 3 of the Star Wars movies. Although, obviously, Alec Guinness's participation in the second 2 movies was not substantial, but still, he was credited as being in them. You can also have graphs that are directed or undirected. So for movies and actors, this is a symmetric relationship. Kevin Bacon being in a film with Tom Hanks is the same as Tom Hanks being in a film with Kevin Bacon. The is in a movie with relationship, we say that's symmetric. Some graphs might have an edge in one direction, but not the reverse. Good example, Google+. Jamie circled Felicia Day. Felicia Day has not circled Jamie. Twitter, Jamie follows Tom Brady, so there's an edge from Jamie to Tom Brady, but Tom Brady does not follow Jamie. Full disclosure, I actually have no idea if Tom Brady's on Twitter, but if he were, and I were, I would totally follow him, because he's Tom Brady. So we can also combine directionality and weights, and depending on how we combine these, we get interesting results. So, for example, for a graph that's undirected and unweighted, Facebook friendship. Facebook friendship is symmetric. If I friend you and you accept my friend request, then we're friends with each other. There's no such thing as having like one-way friendship on Facebook. Something that's directed and unweighted would be Twitter followers or Google Plus circles. So there's no weighting on these, but they are directed. If I circle somebody or follow somebody, they may or may not circle or follow me back. Something that would be undirected and weighted would be the is in a movie relationship. So this is symmetric, but we could weight it by the number of films if we wanted to. Another example here would be distance between cities. If you're able to drive from Galesburg to Peoria, that's about 40 miles on I-74. And it's 40 miles in both directions, and the interstate travels in both directions, so you can sort of go in either way. So that's undirected, but it's also weighted. It's weighted by the distance of 40 miles. You can also have something that's directed and also weighted. So this would be like, for example, the distances between destinations in Manhattan. So this would have to take into account things like one-way streets. So you might have a mileage distance, but, you might only be able to go eastbound on, 4th Avenue or whatever it is. I don't know anything about Manhattan geography, other than that it has a lot of one-way streets. This would work in downtown Chicago as well. I don't know of any one-way streets in Galesburg, actually, but if there were any, we could sort of do that here as well. There is such a thing as what's called a multigraph. Sometimes you might want to have multiple edges between the same pair of nodes. Graphs that allow this, we're going to call those multigraphs. These can be used to represent, for example, 2 different roads, I-74 and US 150, between Galesburg and the Quad Cities. So, US 150, that's one edge, and then I-74, that's another edge. So we've got 2 nodes connected by 2 edges rather than 1 edge. We're going to call that a multigraph. A hypergraph, this is a graph where a single edge can actually connect one or more vertices to one or more other vertices. So these are typically represented as sets. Here we have edge 3 actually connects vertex 3, 5, and 6 together. Edge 2, this is kind of a traditional edge, connects vertex 2 and vertex 3, whereas edge 1, this actually connects vertex 1, vertex 2, and vertex 3, so that's actually a superset of edge 2. There's situations where hypergraphs are useful. If you talk to mathematicians, they'll probably be able to name a ton of situations where hypergraphs are useful. I actually can't think of any off the top of my head, which shows that, 1, I'm not feeling particularly creative, and 2, I clearly did not spend enough time on this Wikipedia article, but there is such a thing as hypergraphs, and it is kind of good to know. So we've got multigraphs, we've got hypergraphs. Now, unless it says consider a multigraph or a hypergraph as a possibility, assume we aren't talking about multigraphs and hypergraphs. In other words, assume we're talking about a typical graph, also sometimes called a simple graph, meaning only one edge between a pair of nodes is allowed, and edges are only allowed to connect 2 nodes. They're not allowed to connect more than 2 nodes together. So unless it says so otherwise, let's assume we're talking about simple graphs, not hypergraphs, not multigraphs. So some terminology. Vertices and edges are the two principal components of a graph. You have some number of vertices, you have edges that connect them. Some people, notably me, like to use the term nodes instead of vertices. A lot of people that do a lot of networking, teach computer networking, often will end up using the term node. Theoreticians, mathematicians are often much better about remembering to use the word vertex. So I'm going to use node a lot. Your lab is going to use the word node, but it means exactly the same thing. The degree of a vertex, or node, is just its number of edges. So if you hear somebody talking about, well, this node has degree 4, that means it has 4 edges connected to it. And I guess for directed graphs, we would have to define whether we mean edges coming into it or edges going out of it. I guess it's a good idea just to specify. I don't know if there's like an unambiguous interpretation if it's a directed graph and you just say degree. I think we would need to specify in degree or out degree. A cyclic graph can have cycles. So for example, this example graph here has cycles. You can go from A to B to D to H back to A. So that would be a cycle. You can see this is an undirected graph. An acyclic graph has no cycles. So this graph here, it's undirected, but there's no cycles. So you could go from, you know, here to here to here to here. Now you can't then get back to here no matter what path you take. You could sort of go backwards, but you can only get back by retraversing an edge you've already seen. Whereas up here with the cyclic graph, you can take all unique edges and get yourself back to A. Down here, can't do that. A directed acyclic graph is a special kind of graph, often called a DAG. It's directed and there's no cycles. Now DAGs are interesting because all trees are DAGs. So for example, this here is a tree. We've got a root. We can follow nodes to get to new edges. Eventually we get to leaves. There's one path to get everywhere. There's no cycles. This is a directed acyclic graph. Although interestingly, not all DAGs are actually trees. Here's a DAG. It doesn't contain any cycles because from B you would go to C, you would go to D, but then you're stuck here because these are directed edges. So there's no way to sort of get back to B. But this is not a graph because it doesn't have a single root. Every node this is not a tree. It's a DAG, but it isn't a tree because if A is the root, you can't get to B, and if B is the root, you can't get to A. Remember, in a tree, every node is reachable from the root along some path. But you'll hear that term DAG for directed acyclic graph regularly when you start talking about graphs. So other terminology, dense, sparse, and complete. A dense graph is going to have a lot of edges relative to the total possible number of edges. A sparse graph is going to have relatively few edges, so sort of a smaller number of edges. And a complete graph, you can think of this as the densest possible graph. This has edges between every possible pair of vertices. So here we have 1, 2, 3, 4, 5, 6, 7 nodes, or 7 vertices, and every one has 1, 2, 3, 4, 5, 6 edges. So everybody's got 6 edges with the maximum number of edges you can have. So let's say this is a complete graph. Every possible edge is represented. Another concept with a graph is connected or disconnected. So a graph is connected if there's a path from every node to every other node. A graph is not connected or disconnected if there's nodes that are not reachable from each other. So for example, in this graph here, there's sort of 2 components. There's the 1, 2, 3, 4 component, the 5, 6, 7, 8 component. No matter what you do from 1, there's no way to get to 5, 6, 7, or 8. There's no, this is called a cut. There's no way across this cut. So I'd say this is a disconnected graph because there's at least one pair, in fact there's several pair, of vertices where there's no path that goes in between them. So I'd say that's disconnected. Whereas sort of jumping back here, obviously this is connected because there's a path from every node to every other node. You can sort of see that just by if you just sort of take these outermost edges. And in fact, there's a direct edge from every node to every other node, so I'd say that this is connected. So the complement of a graph, if G is a graph with V vertices and E edges, the complement, which is written sort of not G or G with a bar over the top, and you can sort of see this bar was supposed to be above the G, that should be G bar. This has G bar, or the complement of G, has edges between all nodes that don't have edges in G, and no edges between nodes that do have edges in G. So easy to think about this with an example. On the left here, we can see this graph's got vertices A, B, C, D, E, and it's got this particular set of edges. This has none of the same edges that this graph has, and all of the edges that could be here but aren't here. So this graph on the right is the complement of the graph on the left, and similarly the graph on the left is the complement of the graph on the right. So two graphs are isomorphic if you can create a one-to-one mapping or bijection between nodes that'll make the graphs look the same. In other words, can you swap these nodes around and get back the same graph? So down here, you can create a one-to-one mapping. You can map 1 to A and 2 to B and 3 to C and so on, and that would convert this graph here on the left into this graph on the right. Now you might need to sort of rearrange the nodes a little bit, but that doesn't really matter. The placement of the nodes in a graph is not actually significant. All we really care about are the vertices, the edges, possibly the directionality, possibly the weights. How you draw the graph, where you lay it out, doesn't really matter. So you can make a one-to-one mapping to turn this graph on the left into this graph on the right, and similarly we could sort of map back as well. Now, these three graphs here are isomorphic. They're actually the same graph. They're just drawn differently. They're actually three versions of exactly the same graph. Because if you look at one, it's got edges to 2 and 4. Here, 1 also has edges to 2 and 4. Here, 1 also has edges to 2 and 4. And so on. This middle graph's just kind of been twisted, but it's not changing anything substantial in the structure. It's still got the same nodes and the same edges. This graph's just been drawn with like crazy looking edges. There's actually no standard way to draw the edges. You can draw them looking like whatever you want. What matters mathematically for a graph is just that there's an edge or there's no edge. And if it's a weighted graph, we care what the weight is. So all three of these graphs are actually isomorphic. They in fact depict the same graph if you were to break these down into code or mathematically. They're going to look exactly the same. And similarly over here, these are the same graphs because we can create a mapping between them. So let's see. All right, moving on. Infinite graphs. So most graphs are finite, which means we have a fixed number of nodes and edges that we know ahead of time. Now it is possible to have an infinite graph. There's different ways to do this. Kind of in my mind, the simplest way or best example of this is if you have a graph that's generated programmatically. So a good example of this, nodes represent the state of a chessboard, and the edges represent possible moves. Now, because it's possible to move certain pieces back and forth in chess, it's actually possible to recreate the same board state that you just had previously, if kind of both players do this. And so because that's possible, if you're not careful, you could actually have some sort of infinite graph, or an infinite tree, really, at this point. But that is something significant to keep in mind. If you're generating things programmatically, it could be infinite. We'll discuss this more when we talk about artificial intelligence. But that is something to keep in mind. It is possible to have an infinite graph, especially if it's generated programmatically. So here's a question. How would you represent a graph? I'll give you a second to pause me and think about that. Awesome. So there's two basic strategies. They're the most common. An adjacency list. Each node contains a list of edges to other nodes. Or an adjacency matrix. You're going to store a matrix of all possible edges and then track whether there's no edge or whether there is an edge. So adjacency list, not so bad. Kevin Bacon's connected to Kiefer Sutherland and Julia Roberts and Tom Hanks, and this is actually Sarah Jessica Parker, who, believe it or not, was in the movie Footloose with Kevin Bacon. And then, of course, Kiefer Sutherland. I can't remember what movie he was in with Kevin Bacon. Somebody will have to point that out to me, because for the life of me, I can't remember what movie they were in together. Damn it. Anyway, they were in a movie together. And then, of course, Corey Haim and Corey Feldman were in Lost Boys. I actually have a special slide for that. Woohoo, Lost Boys! With Kiefer Sutherland. Actually, I should say the late Corey Haim, because I think he just passed away this past year. Anyway, moving on. An adjacency matrix is kind of going to look like this. You're going to have your nodes, the headers for the rows and the columns, and if there's an edge between them, we're going to mark it with a 1, otherwise we'll mark it with a 0. This is obviously for an unweighted graph where we just care that there's no edge or that there is an edge. For a weighted graph, you would substitute these 1s with whatever the weight is. Now, notes for an adjacency matrix, what do we put in the diagonals, and what do we do if we have an undirected graph? Well, what we're going to put on the diagonals doesn't really matter, since nodes aren't really allowed to link to themselves, so we can leave those empty. We're really just going to ignore those. And if we have an undirected graph, that means it's symmetric, so we actually don't need to store half of the matrix. So going back a slide, or going back 2 slides, you can see that this top part of this matrix here actually mirrors the bottom part of the matrix here. And so because of that, we actually don't need to store both of them. We can sort of just store one of them. In languages like C, which don't really have unbalanced arrays very easily, I guess you can kind of fake it. That might not be that useful. But in Java, where you can kind of have triangular arrays, this might actually save you some storage if it's a particularly large undirected graph. So basic graph operations, we want to be able to add a node, add an edge between 2 nodes. We want to be able to remove a node, remove an edge, and we want to be able to ask if there's an edge between 2 nodes, and of course get the cost if it's a weighted graph. And so for those things, we're actually going to do those as clicker questions in class, where we try to figure out what's the complexity of some of these kinds of operations, both in terms of time, what's a runtime going to be, but also in terms of storage, how much stuff do we need to store. So how might we make an adjacency list a little bit more efficient? If we're just sort of thinking about a collection of nodes and a list of their edges, instead of a list, we actually can use a map. So if you know the names of all the nodes, you can sort of look them up with a map. That gives us constant time lookups, and then we can just kind of look through all of its edges to see what it's connected to. So this will kind of look like this. So we sort of look up the key node 1, and then we get a list of what edges it's got in it. So this can actually speed up some of our lookups. We'll talk more about this when we do the clicker questions on runtime. There's 2 basic traversals to traverse a graph. There's breadth first search. The idea with breadth first search is you're going to check all your neighbors before you check your neighbor's neighbors. There's depth first search, where you're going to check your neighbor's neighbors before any of your neighbors. So, you know, given this kind of graph, if we start with Kevin Bacon and we do a breadth first search, that means we would look at Kiefer, Julia, Tom, and Sarah before we look at any of their neighbors. So we would always have to look at Tom before we can look at Meg. There'd be no way to look at Meg because there's no, before we look at Tom, because there's no direct edge between Meg and Kevin. With a depth first search, if we look at Kiefer first, we have to fully explore all of Kiefer's neighbors before we can look at any of Kevin's other neighbors. So if we sort of start here, we're actually going to look at Corey and Julia before we could look at Tom. And in fact, we would just kind of keep going. From Julia, we'd have to look at all of Julia's neighbors before we look at any of Kevin's neighbors. And of course, Tom is one of Julia's neighbors. So basically, if we don't start at Sarah, because she's kind of over here by herself, if we start at one of the other nodes, we're actually going to explore the entire rest of the graph before we ever explore Sarah. So depth first search is another way to go ahead and traverse through this graph. So some pseudocode for breadth first search. This is like vaguely Pythonic, but it's really just pseudocode. So visited, it's a set of nodes we've visited. Our work queue, that's actually a queue, so it's a first in, first out data structure. You can think of a queue as, you know, like a line at the bank. You know, the first person to get in the line is the first one that gets to go up to the bank teller. So we're going to enqueue the start node. We have to know what node to start doing the depth first search at. Now we're going to add that start node to our visited set, so we know, hey, we've already visited the start node, because you only want to visit each node once. You don't need to visit nodes multiple times. And so while this work queue is not empty, and obviously it's not empty, we just added something to it, we're going to dequeue this node. We're going to process it for whatever we need to do in this breadth first traversal. So we might just be printing out the nodes, we might be doing something to the nodes, we might, there's any number of different things we could be doing. So we do whatever that is. Then we iterate through all of X's neighbors. If we haven't visited that neighbor, then we're going to add it to our work queue. And then, nope, we actually don't add it to visited here. right? Because we're just adding them all to the work queue, and then we come back up here, we pull one out, and then process it. And then we add it to the, after we process it, we're supposed to add it to visited. So, yeah, that's really weird that I completely seem to do this wrong. Huh. Well, that's interesting. So the question would be, how would you convert a breadth first search to a depth first search? I'll give you a chance to, pick your answer here. Okay, great. If you said change the queue to a stack, you're correct. That's really the major difference. Work is now a stack instead of a queue, so it's first in, first out. And so if you think about it, looking at your neighbor's neighbors before your own neighbors means, you sort of pop open the first thing you need to process, you sort of look at it, then you add all of its neighbors. But since you're pushing these onto a stack, those are now coming before anything you had previously added. So you're going to sort of be looking at the most recent stuff first. And so the other algorithms that we're interested in are Dijkstra's shortest paths, and we're also interested in the Prim-Jarnik algorithm for a minimum spanning tree. Now for those two algorithms, I started, as you can see, dutifully doing some stuff with Dijkstra, but there's actually a bunch of videos on Dijkstra. I'll link to one or two of them, and you can just go ahead and watch them. But you're going to want to figure out how those graph algorithms work, Dijkstra's, and also, wait, what was the other one? Right, Prim-Jarnik. And understand how those algorithms are going to work for computing a minimum spanning tree or the shortest path from one node to every other node in the graph. Okay, thank you.